Hi, thanks for joining me. Today I've got a cool integral problem I want to show you, and this is from step 3, 2018, and this is problem 8. So I've made a few step videos already. It's the entrance exam you've got to take if you want to study undergraduate maths at the University of Cambridge. Anyway, there'll be a link in the description below if you want to find out more details of the step or applying to Cambridge to do maths or anything like that. Let's get stuck in with the problem. The first thing that this problem says is we don't have to worry about issues of convergence because we're looking at infinite integrals and infinite series. So usually you'd have to worry about convergence, but for this problem it says just assume that everything converges nicely enough and that all the integrals and summations exist. Okay, so part 1, we have this integral I defined to be equal to the integral from 0 to 1 of f of the inverse of x over 1 plus x dx. So f of 1 over x over 1 plus x dx. Okay, where f is just some arbitrary function for which this integral exists. We want to show that I can also be expressed as this thing here, the infinite sum from n equals 1 to infinity of the integral from n to n plus 1 of f of y divided by y times 1 plus y dy, and deduce that if f of x equals f of x plus 1 for all x, then we can also write I in this form here, the integral from 0 to 1 of f of x divided by 1 plus x dx. That's part 1. Now part 2, we want to compute these two integrals here. The first one, the integral from 0 to 1 of the fractional part of 1 over x divided by 1 plus x dx. And the second integral we want to compute is the fractional part of 2 over x divided by 1 plus x dx, so 2 times x inverse. So these curly brackets here means the fractional part, so if you've not seen that before, don't worry. It simply means that for positive integers, which is positive numbers, which is what we're working with, or non-negative numbers, it's just the bit after the decimal point. So for example, the fractional part of 3.2 is just 0.2. The fractional part of pi is just 0.1415 and so on. And then the fractional part of an integer, say 7, that's just 7. Okay, so that's just what the fractional part of the curly braces notation means. Anyway, this is a problem. If you want to have a go at it, pause the video now and give it a go for yourself. And I'm going to jump straight into a solution. Okay, so for the first part of part 1, we want to show that we can write I as this infinite sum here. It's hopefully quite obvious. The first step, we have to do a u substitution where we exchange this x inverse for a y. So we're going to say let y equal x inverse, which is just 1 over x. Of course, that just means x is 1 over y. And then just giving this gives that dx equals minus 1 over y squared dy. Okay, just plugging that back into what we have for I. We then get that I is equal to the integral from, well, when x is 0, remember 0 here is sort of coming from the positive side, so it's 0 plus. So this guy here is 1 over 0 plus, which is positive infinity. And then our upper limit 1, well, when we plug in x equals 1, we get y equals 1 over 1, which is just 1. Okay, f of x inverse now just becomes f of y. And on the denominator we have 1 plus x on the denominator, so that's just 1 plus 1 over y. And then dx becomes this minus 1 over y squared dy. Now, firstly, we can use this minus 1 here to swap the limits of integration because, basically, if you've got a negative sign, you can get rid of it and also swap these things here. So let's get rid of the minus sign, which will change this 1 into an infinity, and this guy here to a 1, like so. And now we can sort of distribute this y squared into the denominator here. So here, this 1 will turn into a y squared, and this 1 over y will turn into a y. So on the denominator, we're going to have y squared plus y, but of course we can sort of factorize it to make y times y plus 1, like so. So if we just get rid of this, and we get y times y plus 1, and then I'll just bring the dy here. Okay, cool. So it's kind of looking very similar to this guy, except we've got an infinite sum here. But what we can do is we can just split this integral and look at it in between all the integers. So this is just the integral from 1 to 2 of this guy here, plus then the integral from 2 to 3 of this guy here, I won't write it again, plus the integral from 3 to 4 of this guy here, and so on off to infinity. Okay, so I've just split this this interval 1 infinity into 1, 2, plus 2, 3, plus 3, 4, and so on, and that's going to give us our infinite sum there that we require. Okay, so that's the first part of part 1. Now let's move on to the second part of part 1. Okay, so we just showed that I can be expressed in this infinite sum notation here. Now what we want to do is show that if f of x plus 1 equals f of x for all x, then I can also be expressed as this integral here, the integral from 0 to 1 of f of x divided by 1 plus x dx. Now, generally with step, if you've just proved a result, you'll probably need to use it. So let's use this to try and prove this thing here with the further assumption that f of x plus 1 equals f of x for all x. Okay, so we're going to start off with this thing here, and we're going to actually write this now in sort of a partial fractions form. So it's now the integral from n to n plus 1 of f of y over y minus f of y divided by y plus 1 dy. So just to check that this guy equals this guy, let's cross multiply by the y plus 1 and the y, so we get y plus 1 times f of y minus y f of y. So the y f of y's will cancel, and we'll just be left with 1 times f of y on the top, and on the bottom we're left with a y times y plus 1. So that thing there. So that's perfectly fine. Now what we're going to do is we've sort of got two integrals here, so we're going to write these as two integrals. This is the this one here is, we'll keep it in the summation form of f of y over y, and then this guy here, the sum from n equals 1 to infinity, the integral from n to n plus 1 of f of y all over y plus 1 dy. Okay, now we can see that this guy here is going from n equals 1 to infinity, but if I sort of do a substitute, oh I forgot to put a dy here, if I do a sort of substitution to make this y into a y minus 1, then this thing will now be an integral from 0 to infinity. So if I now do this, u equals y minus 1, so that of course just means du is equal to dy. This thing here becomes the sum from n equals 1 to infinity of the integral from n minus 1 to n, because when y is n, u is n minus 1, and when y is n plus 1, u becomes n plus 1 minus 1, which is n, of f of y divided by y, but f of y is just f of u plus 1, but f of u plus 1 is just f of u. And on the denominator we get a y, which is just u plus 1, and then that's du minus the sum from n equals 1 to infinity of the integral from n to n plus 1 of f of y over y plus 1 dy. Now, if we just have a look at this thing here, we're starting from n equals 1, but this sort of the smallest limit is 0. So this, in fact, is the integral from 0 to infinity of this guy here. And this thing here is the integral from n equals 1 to infinity of this guy here. Excuse me. But we can see that the integrands are exactly the same thing, except here we've got a u, here we've got a y, but they're both dummy variables, so it doesn't matter. So here we're doing the integral from 0 to infinity of something, and here we're subtracting off the integral from 1 to infinity of that same something. So all we're going to be left with is the integral from 0 to 1 of that something, and that something is just f of x over 1 plus x dx. Because again, u, x and y are dummy variables, doesn't matter what I call it. Basically, we've shown that I now equals the integral from 0 to 1 of f of x divided by 1 plus x dx, provided that f of x plus 1 equals f of x for all x. Great, that's part one done now. Now let's move on to part 2, where we actually have to compute two specific integrals. Okay, so the first integral from part 2 asks us to compute the integral from 0 to 1 of the fractional part of x inverse divided by 1 plus x dx. Now, we had initially the I being defined to be equal to the integral from 0 to 1 of f of x inverse divided by 1 plus x dx. And then we showed that if f also has this property that f of x plus 1 equals f of x, then I can also be expressed as the integral from 0 to 1 of f of x divided by x plus 1 dx. So we definitely want to try and use this. So first thing, just looking at this, it's quite clear to see that we should let f of x just equal the fractional part of x, because obviously if this is the fractional part of x inverse, then that corresponds to f of x inverse here. So we've got this integral in this form here. Next, we want to check that f of x plus 1 equals f of x, and then once we've done that, if that holds true, then we can apply what we proved before, and then write this as a different integral. So the integral of just the fractional part of x as opposed to the fractional part of x inverse. But firstly, we've got to check that f of x plus 1 equals f of x for all x. But that's kind of straightforward, because f of x plus 1 is just, or let's just give an example, which will hopefully illustrate it. F of pi, for example, is just the fractional part of pi, which is 0.14159 something. But of course, this is the same thing as the fractional part of 4.14159 something, and that of course is just the pi plus 1, and that of course is f of pi plus 1. Okay, so that's just to sort of illustrate it. I'm not sure how detailed you'd have to go to claim that f of x equals f of x plus 1, but hopefully it's quite obvious. It's essentially you're adding on an integer, so you're not going to change the bit after the decimal point. Okay, so f of x plus 1 does indeed equal f of x for every x, so that means we can apply this result, And then that means that this integral here is just the integral from 0 to 1. Now, as opposed to f of x inverse, we just write f of x. So that's just the floor of x, the fractional part of x divided by 1 plus x dx. But remember, this is just a bit after the decimal point. But because x is between 0 and 1, that just is x. Because x, when in between 0 and 1, x could be 0.26. But the fractional part then of x is just 0.26, so just x. So this thing here is just the integral from 0 to 1 of x divided by 1 plus x dx. And there are a bunch of different ways you can evaluate this. What I'm going to do is add 1 and minus 1 from the numerator. So I can write this as the integral now of 1 plus x minus 1 divided by 1 plus x dx. But of course, this is the integral from 0 to 1 of 1 minus 1 over 1 plus x dx. And I'm running out of room. This thing here, the integral from 0 to 1 of 1 is just 1. And then we get a minus, and then the antiderivative of 1 over 1 plus x is just log, or the natural log of 1 plus x. And that's evaluated from 1 to 0. Obviously, when we plug in 0, we get log of 1, which is 0. And when we plug in 1, we get 2. So this is 1 minus log 2. Let's just write it there. Okay, so that's our solution for the first part of part 2, the somewhat easier integral. Now let's get on to the second integral, which requires a little bit more thinking. Okay, so the final integral we want to compute is this guy here, the integral from 0 to 1 of the fractional part of 2 x inverse, so 2 over x, divided by 1 plus x dx. We're going to use a similar method to what we just did with the previous integral. So we're going to let f of x equal the fractional part of 2x, like so. Okay, so of course this thing here is in this form here. And now we've got to check that f of x plus 1 equals f of x, and it's going to be something very similar to what we had before. Well, let me just quickly write it out. F of x plus 1 is just 2x plus 2. But again, the fractional part of something when you just add on an integer is going to stay the same because the bit after the decimal point doesn't change when you add on an integer. So this is just going to be the floor of 2x, and that of course is just f of x. Okay, so we do have the f of x plus 1 equals f of x for all x. So then that means we can write I in this form here. So this equals now the integral from 0 to 1 of f of x, which is just the fractional part of 2x divided by 1 plus x dx. Now we've got to be a bit careful here because before we just said that because x is between 0 and 1, the fractional part of x is just x. But that's not true because if we look at, for example, 0.75, which is in this range here, 2 times 0.75 is 1.5, and the fractional part of that is just 0.5 as opposed to 0.75. But we can overcome this issue by splitting this integral into two sort of different regions. So this is the integral from 0 to a half of the fractional part of 2x divided by 1 plus x dx, plus the integral from a half to 1 of the fractional part of 2x all over 1 plus x dx. And the reason we want to do that is now we look at the fractional part of 2x in this range here. Well, x is between 0 and a half, so 2x is between 0 and 1. So the fractional part of 2x will certainly just be 2x for this first integral. So this is the integral from 0 to a half of 2x all over 1 plus x dx. And then this second one here, because x is at least a half and at most 1, that means that 2x is between 1 and 2. So then that means that the fractional part of 2x is just going to be 2x minus 1. So this is plus the integral from a half to 1 of 2x minus 1 over 1 plus x dx. Because there isn't enough space, let me just clear up the whiteboard and I'll finally compute these last two integrals. This is just routine, but let's quickly get into it. Okay, so we just showed that the integral we want to compute, the integral from 0 to 1 of the fractional part of 2x inverse over 1 plus x dx, equals the sum of these two integrals here. As I said, these are very standard, so let's just get stuck in. This thing here we can write as the integral from 0 to 1, or we can bring the 2 out, 0 to a half, of x over 1 plus x. That is just 1 minus 1 over 1 plus x dx. And a similar sort of thing here, I'm going to add 3 to the numerator and then subtract 3 from the numerator. So this then becomes the integral from a half to 1. When I add 3, I'm going to get a 2x plus 2 on the numerator, but 2x plus 2 divided by 1 plus x just equals 2. And then I'm going to have to subtract off the 3 that I added on, so I get a minus 3 over 1 plus x dx, like so. And now these things I can just sort of compute the antiderivative of. This thing here is 2 times the antiderivative of this is x minus log 1 plus x, and that's between a half and 0, plus x, 2x minus 3 log 1 plus x, and that's between 1 and a half, like so. Plugging in a half into this guy here, I get 2, a half minus log 1 plus a half, and when I plug in x equals 0, I get 0 minus log of 1, which is just 0, so when I plug in 0, I get nothing, so I just need to worry about when x is a half, so this is just 2 times a half minus log 3 over 2, like so, and then this guy here is just, when I plug in x equals 1, I get 2 minus 3 log 2, and then when I plug in a half, I get 1. So of course I'm subtracting off a half, so minus 1, then minus 3 log 3 over 2. So that's plus 3 log 3 over 2. And now we can sort of bring these terms together. We've got a minus 2 log 3 over 2 plus 3 log 3 over 2, which gives us a log 3 over 2. A 2 times a half is a 1, minus this one here cancels, and we're just left with this plus 2 here. And then of course we've just got this minus 3 log 2 term left. And if you want to bring all the log terms together, we can just do 2, this constant here, and then log 3 over 2 minus 3 log 2. But 3 log 2 is just log 2 cubed, which is log 8. So we got log 3 over 2 minus log 8. So that's log 3 over 16. Plus log 3 over 16. Or you could write that as log or minus log 16 over 3, whichever you prefer. Anyway, that's how we compute the second integral. As I said, this bit was just sort of standard, a bit boring, nothing interesting there. But how you compute all the integrals at the end is quite nice. How we showed this cool trick, and then an integral or two integrals which seemed quite difficult to evaluate, we could evaluate knowing this trick that if f of x equals f of x plus 1, we can write this integral in this nice way. Anyway, thanks for watching. I'll catch you in the next one. Have a great day.